Well, hello there, ladies and gentlemen. We did the isotopes and radioactivity notes, but I have a feeling we did them too quickly and that some of it flew right by. If you will open your purple notebooks to page 40, again, page 40. If I'm going too fast, feel free to pause as we go, and there are going to be questions built into this video along the way. So, as we go across the periodic table and more protons increase, the nuclei of atoms need more and more neutrons to keep them balanced. But eventually, the nucleus just has an unstable amount of protons and neutrons. And that's at 83. Once we hit element 83, everything after that becomes unstable. And since 83 is bismuth, and right before that is lead. Lead is very stable. These unstable nuclei, we say that they're radioactive. That just means they break apart. The nucleus is unstable and it breaks apart. When it breaks apart, it's going to break into smaller pieces. We're going to talk about the types of radioactive decay. This process of finding out that atoms were breaking apart was kind of discovered by Mary Curie, heavily investigated, and through her research, we discovered a lot of elements. She discovered radium and polonium, and she named polonium after her home country of Poland. And Mary Curie is the only person to have earned not one, but two Nobel Prizes. So there are three types of radioactive decay that we teach you in chemistry. They are alpha, beta, and gamma. These three decays, when written in alphabetical order, A, B, and G, are also written in order of increasing danger, increasing power in terms of like what you have to worry about getting exposed to. If you get exposed to alpha particles for a couple of minutes, you might get a little skin burn. If you get a high concentration, if you get exposed to a high concentration of beta particles, that's going to be worse. High concentration of gamma particles could be horrible for you. Let's talk about what these are. An alpha particle is really just the helium's nucleus. So it doesn't have any electrons, it's two protons and two neutrons. It's just the nucleus. Whereas the beta particle is just an electron. It's an electron that escaped. It's a free electron that flew away from an atom and now it's just an electron because it got too excited. And then gamma is actually a type of radiation, like electromagnetic radiation, like waves of light, but it's very high energy. So it's high energy radiation. We often talk about half-lives when it comes to radioactivity, and the most common half-life thing we talk about is not, am I recording? Am I recording? Yes, I am. The most common type of half-life we talk about is radioactive decay. And okay, I'm gonna have to cut that out. Okay, starting again. Often when we're talking about radioactivity, we deal with half-life. And half-life is the idea that you are losing half. And so maybe we're just gonna kind of put a time frame here. We're gonna go 0, and then 7 seconds, and then 14 seconds, and then 21 seconds, and then 28 seconds, and then 35 seconds. So you notice that my time frame here isn't changing. Each of these is 7 seconds apart. So those are each seconds. Now, so the time component in half-life does not change. So each of these things is 7 seconds apart. Now, what does change is the amount that is lost. So let's say that you start off with 600 grams of uranium. And this data I'm throwing up here is fake for those of you who don't know that. You have 600 grams of uranium, and then 7 seconds go by, and now you have 300 grams. So the other 300 grams that you just lost were radioactive. The nucleus broke apart and gave off radiation, and it's no longer uranium, it's a lighter element. In the case of uranium, it becomes thorium. So of the original 600, 300 grams decayed and became thorium. And then 7 seconds later, you lost half of that. So now 150 grams are left behind. And then 7 seconds later, You lost half of that, and now 75 grams are remaining. And then 7 seconds later, ooh, math's getting harder, 32.5. You know what? I'm just going to say 37 grams. That's not 38 grams, about half. It should be half. My math just got slow there. And then 7 seconds later, 19 grams. So in a whopping uh, 35 seconds, the mass has dropped by half many, many times. And that's what half-life is really interesting about it, is that it represents the amount that's lost. Let me slide that down here as a time component, and that time component doesn't change, where the mass does change, and it changes by halves. It keeps dropping by a half. Um, in our chart on page 41, which here it is right here, we see the mass is starting at 80. Half of 80 is 40. Half of 40 is 20. Half of 20 is 10. Half of 10 is 5. Half of 5 is 2.5. Half of 2.5 is 1.25. You just keep dividing by 2. All right. And then on here, we have the time component. So to go from 80 to 40, bing, hit the line and come down. 5 days. Okay. It took 5 days to drop from 80 to 40. Now let's take half of 40. Half of 40 is 20. Bing! There we're at 20, and we're also at 10 days. So it took another set of 5 days to lose half. And now let's go 20. What's half of 20? 10. Now we're at 10. And look, it took another 5 days. So you can see that every 5 days, they're losing half of whatever's present. And this is how Half-Life works. You have a set quantity of time, and you keep losing every time that amount of time occurs half. It's very common with carbon dating. There is an isotope in carbon of one of the carbon atoms called carbon 14, and you lose half of your carbon 14 every 1,500 years. So if a substance that was supposed to have 100 grams of carbon 14 when it passed away, you could say, well, 100 grams, now it has 50 grams, this much time has passed. Now it has 25 grams, this much time has passed. You can also do that in reverse. You could say, okay, if I have 25 grams now, 1,500 years ago, I had double. And then 1,500 years ago, I had double of that. So you can also build it backwards. It works in both directions. So that's why Half-Life is a pretty commonly used tool. So now if you flip to page 47, we're going to talk about average atomic mass and how it's really a weighted average instead of the average you're used to. Like if someone told you what's the average of the number 10 and the number 9, the average of the number 10 and the number 9 is 9.5. It's right in half of the two. But what if they said, what's the average of 10, 10, 10, 10, 10, 10, 10, 9, 9? That average has to take into account that the number 10 is occurring a lot more than the number 9. You give the number 10 more weight, a greater factor into the calculation. So how would you do that? Well, here you go. You go, the 10 appears multiple times and the 9 only appears twice. And since this number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, since that number appears 10 times, we're dividing by 10 to get the average 9.8. Or we could do it this way. The number 10 appears 8 times, the number 9 appears 2 times, and that would be 10. There's also a third way we could do it. I'm going to type this in here right now. The number 10 is 80% of the sample, and the number 9 is 20% of the sample. And since those are percentages, we would divide by 100 afterwards. And that's closer to what we're going to be doing. Oops, a mistake. Again, there we go. So this is the same math. We're still going to get the same answer, 9.8. We're often going to use percentages in our examples. And let's go ahead and do the discussion about atomic mass. So we talked about how isotopes Isotopes of protons plus neutrons gives you mass number. We talked about isotopes could come in different masses, that there might be a mass of 12 for carbon, a mass of 13 for carbon, and a mass of 14 for carbon. Well, how do they average those together? They do a weighted average. They take the mass of the isotope, they multiply it by the percentage, and they then add them together and divide by 100. So here's the example here. Let's say 95% of all carbon had a mass of 12, 4.9% of the carbon had a mass of 13, and a very tiny percentage has a mass of carbon 14, that radioactive carbon. And so you take the mass and the mass and its percentage, the mass and its percentage, you add it all up, you divide by 100, and you get the average. Now, I'm going to tell you, this should have matched what's on the periodic table, but our numbers are slightly off here. I think our percentages are off for this right here. But the weighted average factors in those percentages to make sure that we get a better average than just a straight up average like we normally do. Now, at the bottom of page 47 is the only example we're doing on this, and that is on chlorine. They say you have 75% of your chlorine has this as its mass, and 24% of the chlorine has this as its mass, and calculate the average. So go ahead and think about what we just did in the previous problem, where we have the mass percentage, we added them up, and we divided by 100. Well, that's what we need to do here. We have the mass and the percentage. We have the mass and the percentage. We need to add them together, divide by 100, and let's see what you come up with. All right, you should have come up with this as your setup, right? So if you come up with that as your setup, now do the math. Calculate the average of these two isotopes. Did you get 35.46? You should get between, this is 35, 34.9, this is 37, 36.9. So you should get a number between those two because you're averaging. And we did. And if you look at the periodic table, we got an answer very close to what chlorine is on the periodic table. Chlorine on the periodic table is 35.45. Okay, so you need to practice both radioactivity exercises and average atomic mass. So you need to go in your notebook and do a couple of questions from page 49. The very beginning of 49 has a mixture of average atomic mass and radioactivity. You should skip questions 2 and 3. Skip questions 2 and 3. All right, we'll see you all tomorrow.